Uh, Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, welcome to Technical Session 5E. My name is Amog Damdere, and this session will be moderated by me. On behalf of the Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you all to the 11th International Congress on Information and Communication Technology, ICICT 2026, London, UK. The 11th edition of this conference is being organized in hybrid mode. The physical event was held yesterday in London. The virtual event is being held through Zoom from the 25th to the 27th of February 2026. I hope all of you will enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for the presentation and 3 minutes for questions and answers. On the completion of 10 minutes, I will be raising a gentle reminder. There is another request to all the participants that all of you stay connected with us until the closing remarks are done. If you have any queries or updates, you can write it to me in the meeting chat box. Just before we start the session, I would like to introduce you guys to the session chairs. Dr. Kankaran Panipong. He is currently an associate professor at the Faculty of Business Administration and Information Technology in the Rajamangala University of Technology, Taiwan, in Bangkok, Thailand. His expertise is in higher education, lifelong learning, and adult education with a focus on fostering collaborative and innovative teaching methods. Passionate about enhancing learning experiences, he actively promotes lifelong learning and engages in developing effective teaching strategies to empower learners in a dynamic educational environment. I welcome you, sir, and request you to give us your opening remarks.
Okay. So I have to say, good night in Bangkok, Thailand, but and have to say, good evening in London. So we're proud um to join a sixth present today. So could you please run one by one following the agenda?
Sure, sir. So our next session chair is Dr. Anuradha Yenkik. She is I'm really sorry. She is currently working as an assistant professor at the Department of Computer Science Engineering, Artificial Intelligence in the Vishwakarma Institute of Information Technology. She has published more than 30 research articles in reputed journals with SCIE, Web of Sciences, Scopus Indexing. She has also published many book chapters many book chapters and patents. Her research interests include data science, machine learning, artificial intelligence, deep learning, and parallel computing. I welcome you, ma'am, and request you to give your opening remarks.
Yeah, thanks, Amog. So, good evening, all the researchers who have joined to this meeting, and also good evening to the session chair, co-session chair. So, thank you for giving this opportunity, and look forward for all the knowledgeable presentations. All the best.
Thank you so much, ma'am. So we can now start with our presentations. Our first presenter for today is Vishalini Pirathap from the SLIIT Northern University in Sri Lanka. And the title of the paper is An Adaptive Maintain. I'm really sorry. The title of the paper is An Adaptive Maintainability Complexity Score for Multi-Language Software Systems. Ma'am, I request you to kindly unmute and start presenting.
Yeah, thank you. Am I audible? Can you hear me?
Yes, yes.
Okay. I will share my screen. Yeah, ma'am. Unable to share the screen. I need to approve from the session.
Okay. So I think Amok, can you help her?
Yes. Among I couldn't able to share the slides.
I'm really sorry, ma'am. I was sharing the screen. You can go right ahead.
Yeah. Okay. Thank you so much. Give me a 1 minute. Can you see my screen? Ma'am, can you see my screen?
Yes, it's now
Yes,
visible.
yes, yes.
Yeah.
Okay. Okay. It visible, no? Right. So, good afternoon, everyone. I'm Ishani Pradap from Slate Nadanj University, Sri Lanka. I'm working as a lecturer here. So today I will present my work titled An Adaptive Maintainability Complexity Score for Multi-Language Software System. So actually, this research proposed a language-neutral adaptive maintainability metric designed for heterogeneous software environment. So here my motivation, so modern software system increasing heterogeneous. So project combine that multiple programming language, which often leads to inconsistent metrics behavior across implementation. So traditional size-based metrics fail to capture that hidden cost, such as cognitive, that effort and design coupling. And also, more importantly, that coupling introduce nonlinear risk. So the strong interdependencies create ripple efforts that linear aggregations models underestimates. So the problem, so here we face three existing composite research. We found the three main problem that are static weights and it have a linear aggregations and language bias. Therefore, we need a maintainability matrix is language independent, interpretable, adaptive to metric impact, and sensitive nonlinear coupling efforts. So the research gap, so the current approach, it's a unified language neural maintainability model. So most of the fixed weight schemes, they rely on linear aggregations and the inadequate model ripple effort caches by coupling. These limitations motivate the proposed AMCS framework. This is my proposed framework. So here that AMC integrate nonlinear coupling penalty metrics. So the frameworks combine that conjunctive structural size, maintainability, and coupling dimensions into a single adaptive composite measure. That methodology here, I follow the 5-step pipelines. First, the score code written in Java, C Sharp, pass into an abstract index tree. Second, these ASTs are transformed into command intermediate representations to ensure language neurality. And third, we extract 5 metrics like a ICB, that VG complexity, cyclometric complexity, lines of code, MI, and CBO. After normalization, adaptive weights are computed dynamically. Finally, the nonlinear coupling penalty, we produce that AMCS score. So the framework is evaluated using functionally equivalent implementations and sensitive experiments. So I choose these 5 metrics to my AMCS framework, that ICB for the conjunctive, VG for control flow, that means the cyclometric complexity, and lines of code, then MI, finally the CBO. So the core mechanisms we follow this AMC. First, this metric normalization. All the metrics are scaled to 0 to 100 using the threshold-based normalization, because higher MI value indicate better maintainability. It is inverted. So this ensure that higher normalized values consistently represent higher maintainability risk. Then second one, adaptive weighting. So each matrix weight is proportional into normalized risk contribution. This means metric which higher risk automatically receive greater influence in the final score. So this makes the framework adaptive and system responsive. Then the third one is a nonlinear coupling penalty. So even small increase of dependencies can significantly increase the maintenance effort. Therefore, the AMCs introduced that exponential coupling penalty. This model repeal affect behavior realistically and prevents linear underestimate of coupling impact. So the final AMC's final that formula is that weighted aggregation normalization matrix incorporating the exponential coupling penalty. The score increases monolytically with a maintainability risk and is grouped into a good, moderate, and high risk pattern. So that in this research, we introduced that intermediate representations IR as well, because we ensure the language neurality code from the Java, C, and C+, C Sharp, into a common intermediate representation. It's called a IR, intermediate representation. So it synthetics difference while preserving that symmetric structure. So metrics are extracted consistently from their representations, ensuring the fair cross-language comparisons. So we'll move to the results. So this AMC score, so it's highly, you can see here that it's highly giving the Java giving a 24.9 score, and C is 24.3 score, and C Sharp 25.1 score. So all fall within the good maintainability band. So that is demonstrate cross-language consistency and validate the normalizations and IR approach. Then these tables demonstrate the language consistency and comments that AMC's response non-linear to increasing complexity and coupling. Then these also the continuous results from that last slide. Then here, we are sensitive analysis was performed by incrementally increasing complexity and coupling. As branching structure and dependencies increase from V0 to V3, that AMC is from 23.7 to the V3 29.8. So the increase is nonlinear, confirming the effectiveness of adaptive weighting and exponential coupling model. So the conclusion, so these AMCs provide the language neural adaptivity and interpretability models. It dynamically adjusts metrics, influence, and models nonlinear coupling impact. The experimental results demonstrate consistency, adaptability, and partially applicability. So this the AMCS represents a step toward realistic and scalable maintainability assessment in a modern multi-language system. Thank you.
Thank you. So, can I ask you one question?
Yeah.
Yeah. So, what are the applications of this research studies?
So
In
I
real
got
life,
from so I done this research under my supervisor from the SLIT. So he done some researches based on this complexity matrix and everything. For that I took the research that I took my reference from that one man. Is that the answer for your question?
Yeah, but where it will be applicable, like in which scenarios this kind of research will be useful?
Yeah, so here nowadays that IDs, they are checking the complexity matrix. So we can implement this as an extension. We can introduce this matrix to in the extractions when the developers doing the coding, they can use and they can evaluate their coding complexity. Also nowadays they are using that AI to writing a code. So AI can be write various ways. So we can use to measure whether the codes are quality.
Yeah. Okay. Thanks, Vishali.
Thank you.
And yeah, best wishes for your research.
Thank you, ma'am.
Any other questions for our presenter?
Yeah, I'm done.
Okay, thank you so much, ma'am. We can go right ahead.
Oh, sure.
Okay. So our second speaker for today's session is Aryaman Jain from the Bhavan Vidyalaya in Chandigarh, India, and the title of his paper is An Architectural and Performance Analysis of Deep Learning Frameworks. Aryaman, I request you to kindly unmute yourself and start presenting. Okay, apologies. I think Aryaman hasn't joined yet. We can move right ahead. So our next speaker would be WMNSK Yatigamana from LOLC Technologies Limited in Sri Lanka. And the title of her paper is Bringing Transparency to Low-Code/No-Code QA with Explainable. Ma'am, I request you to kindly unmute and start presenting.
Thank you for inviting. So I will let me share my screen.
Sure, ma'am.
Okay. Hope my screen is visible to you.
Yes, ma'am, it's visible. You can start.
Okay, so good afternoon. So I'm Nimeshwari Yatigamana from LIC Technologies. I'm working as an Oracle consultant. So here I'm going to present about my research paper, Bringing Transparency to Low-Code, No-Code QA with Explainable AI. So my paper ID is 804. I'm continuing. So here is my content. And okay, so I'm go with the flow. Okay, so at the introduction. So the low-code, no-code platforms are rapidly transforming. So how enterprise applications are built. Today, operational workflows such as approval, onboarding processes, financial routings, and compliance managements are increasingly developed by citizen developers using visual tools instead of traditional programming languages. The shift significantly accelerate delivery and reduces development cost. However, it also reduces new challenges. Many of these workflows are business critical. They difficulty affect governance, financial processes, and regulatory compliance. Yet, they are built without traditional coding visibility and often without rigorous engineering controls. As adoption increases, ensuring rigorous and the transparent quality assurance in LCNC environments become essential for organizational trust and governance readiness. Okay, so when it's come to problem statement, the quality assurance in LCNC workflows presents several structural challenges. First, there is no source code visibility since logic is embedded in visual components. Second, execution behavior is often runtime dependent, meaning many behaviors only imagined during the actual executions. Third, boundary conditions and exception paths are typically under tested because most validation focuses on nominal business flows. Finally, there is limited stakeholder interpretability. Even when automated testing is used, outputs are often and difficult for non-technical stakeholders to understand. The result is reduced trust, delayed release decisions, and increased governance risk. So the traditional QA techniques designed for text-based programming and do not directly apply to visual declarative workflows. So when it comes to the research gap and research questions, when analyzing existing research, we identify a significant gap. There are studies on quality assurance in low-code, no-code systems, automated testing methods, software compatibility metrics, explainable AI technique likewise. However, these approaches are typically explored in isolation. There is currently no platform natural explainable QA framework for LCNC workflows that integrates automation with interpretability. This led to the following research questions. So here I have three research questions. First one is how to model LCNC workflows in a platform natural form. Second question is how to achieve high path coverage with minimal redundancy. The question 3 is, does explainable testing improve stakeholder understanding and resolution time? So the objective of this research is to design and evaluate an AI-driven explainable testing frameworks that converts LC&C workflows into the platform natural intermediate representation, automatically generates and executes compressive test cases, applies explainable AI reasoning to interrupt execution traces, and then delivers role-specific reports for citizen developers, QA engineers, and execute likewise. So the ultimate goal is not only automation, but the governance aligns transparency, LC&C validation.
Can you actually go to the proposed methodology and results section, please?
Sure. Okay, shall I start from here?
Yes, please.
Okay. So at the proposed framework, when we come to the proposed framework, to address this gap, I developed an AI-driven explainable testing framework. The framework consists of 6 stages. So the first one is workflow ingestion, intermediate representation construction, automated test generation, control execution, explainable AI reasoning, role-specific reporting. So this pipeline integrates the rigorous workflow validation with transparent stakeholder-oriented explanation. To formalize the problem, the LC&C workflow suffers from the no source code visibility, runtime dependent behavior, weak boundary and exception coverage, poor stakeholder integrity. So these issues collectively reduce governance confidence and delay release decisions. So my framework is designed to directly address these challenges through structured abstraction, automated validation, and explainable reporting. Okay, so the first technical contribution is workflow abstraction. So I extract core workflow elements such as triggers, actions, conditional branches, data bindings, likewise. So these are transformed into a platform natural intermediate representation, preserving control, flow structure, and decision systematic. So using this representation, the framework generates functional test cases, boundary condition test cases, exception-oriented test cases. So to control redundancy, I apply equivalence class grouping and path prioritizing for this. So across evaluated workflows, the framework generated an average of 24 test cases per workflow, achieving complete path explanation while minimizing unnecessary execution overhead. So the explainable AI engine transforms execution traces into interpretable evidence. So instead of simply reporting pass or fail, the system produces casual reasoning chains, decision path mappings, natural language explanations, annotated workflow visualization like this. So this enables stakeholders to understand what failed, why it failed, which decision path triggers the failure, and how the logic contributed to the defects. The focus is on transparency, interpretability, and governance alignment. So the framework was evaluated using Microsoft Power Apps, a data set of 147 real-world enterprise workflows. So this result demonstrates using strong performance. So the 100% complete path exploration, so average 24 test cases per workflow, readability score of 8.7, readability score of 8.7, then the completeness of 96.3%, accuracy of 98.1%, visual visibility of the 97.8%. So likewise, all the explanation quality metrics exceeded predefined benchmarkers. So These findings indicates that the framework achieves both technical rigorous and the high interpretability. So yeah, at the comparative effectiveness, I compared the framework against manual validation and baseline scripted the platform native automation. So the improvements were sustained. So the 34% higher defect detection. So here and the 42% reduction in test time. 61% reduction in resolution time, 61% improvement in stakeholder compression. So the explainable reporting significantly reduced cross-role coordination frictions and the accelerated root cause analysis. So this demonstrate that combining automation with explainability yield measurable operational benefits. As a future work, so here the future research will extend the framework across multiple LC&C platforms such as AppSheets and Salesforce. So here I also plan to conduct large scale and the industrial validation studies here. So future enhancement includes like adaptive machine learning based test, prioritization, integration with CI/CD pipelines, standardized LC&C QA benchmarkers, so, and the enhancement interactive role-specific visual explanations. Okay, so this is the final topic, contribution and conclusion.
Okay,
So
that is fine.
yeah.
So when you have compared the results, have you taken any reference from the existing research, or you have compared with your result with like with training and testing within yourself only?
No, I get this from other research papers also. So here, here are the few literature review that I have focused on here. So my comparative evaluation was conducted against two practical baselines. First one is manual validation approaches commonly used in LC&C environments. And the second one is platform native scripted automation method. So I did not compare against the specific published research framework because based on my literature review, there is currently no unified platform natural and explainable QA framework for LC&C workflow that integrates automation and interpretability in the way of approach does. So instead, I perform the comparison using the same workflow dataset that I mentioned at 147 real world Power Apps workflows. So from that, so the evaluation was not just internal training. So testing with my system, it was controlled comparative study against existing industry practice approaches applied to the same workflows. Is that the answer for your question? Hello, ma'am.
Yes, yes, yes.
So I have a few questions to ask you. So
Okay.
how can this system reduce compliance and regulatory auditing risk within the organizations? And another thing, from a digital governance perspective, how does transparency in low code, no code environment impact software accountabilities?
Yeah, so this system reduces compliance and regulatory auditing risk in a few primary ways. So I can say the evidence-based validation. The traditional LC&C validation often produces simple pass or fail results, or it gives the log outputs. So my framework generates structured trace-based evidence like which workflow paths were executed, which boundary and exception causes were tested, what decision logic was triggered, why a failure occurred, likewise. So this creates an auditable trail of validation activity. And then the compressive path coverage, including edge cases. So the compliance risk often arise from the untested boundary conditions and incorrect conditional routings like this. So my framework ensures the complete path explanations, systematic boundary conditioning testing, uh, exception oriented test generations likewise. So and also there is stakeholder interpretable reporting also. So auditors and compliance officers are typically non-technical stakeholders. So instead of technical logs, my system provides human readable explanations and annotated workflow visualizations, governance aligned dashboards likewise. And also there is a faster root cause analysis. When defects are detected, the explainable reasoning engine identifies like the extract decision path, triggering conditions, causal chains likewise. Yeah. Hope I have the answer for your questions also.
Oh, thank you. So happy
Okay.
recent. Thanks.
Thank you.
Any more questions for our speaker?
So is the next to presenter?
Yes, sir. We can move right ahead. So one of our previous presenters has joined us back. Just a second. Okay, so our next speaker is Aryaman Jain from Bhavan Vidyalaya in Chandigarh, India. And the title of his paper is An Architectural and Performance Analysis of Deep Learning Frameworks. Sir, I request you to unmute and start presenting.
Just a second. I'll just start sharing my screen. Hi, is my presentation visible?
Yes, it's visible. You can start.
Sure.
Okay, great. So good afternoon, everyone. I'm Ariman Jain, and I'll be presenting my survey paper co-authored with Dr. Rohini Arora and Dr. Sumit Kaursera from the Conestoga College. Our survey is titled An Architectural and Performance Analysis of Deep Learning Frameworks. So the format of my presentation will be as follows. Firstly, I'll begin with the introduction, categorizing the status quo and the research question that we set out to answer, followed by the parameters or the criteria that we use to evaluate each framework. Then we move on to a brief overview of the different frameworks that we consider on this study, divided into two categories broadly, then followed by a comparative analysis. So this includes a qualitative comparative analysis, which in the form of a comparison table, and a quantitative comparative analysis in the form of a literature review. Then finally, based on that, we present our insights and our conclusion and our recommendations to developers, and finally ending with the question and answer session. So firstly, before we move on to the research question, I think it's important to categorize the status quo and the state of the field in which our paper is based. So firstly, deep learning right now, as we all know, is being deployed on a massive scale. Frontier models are hitting upwards of 1 trillion parameters. GPT 5.3 is estimated to have about 1.7 trillion parameters. And on top of this, because deep learning performance scales logarithmically with compute and parameters, this number will only grow if the current trend of increasing performance continues. On top of this, these models are being deployed in various fields, including medical imaging, AI assistants, AI-assisted vibe coding, and so many more. So their usage is also on a massive scale right now. So in this status quo, it is imperative that the deep learning framework that we select, keeping in mind the current scale of deep learning and the current pace at which cutting edge research is happening, cutting edge developments are happening, it is imperative that the framework we choose not only provides good performance in training and inference of these models, but has facilities that allow us to incorporate latest developments and provides a good developer experience so that one can rapidly prototype and conduct experiments. So in this background, the question arises that with so many deep learning frameworks available, which one is the best option for which use case? So to answer that question, we devised 8 broad parameters on which we compare these different frameworks. So firstly is the supported platforms, which includes operating systems and different processor architectures, then licensing and cost. So cost is of course self-explanatory, but in terms of licensing affects the usage to a great degree as well, as it controls what sort of changes you can make to the framework and how you can use it in a commercial setting. Then we move to the supported languages like different programming languages or the user interfaces it provides. And then to fourthly, the compute platform that it supports. So that is NVIDIA CUDA, AMD ROCm, Apple MPS, or OpenCL. All of these are platforms that allow the training to utilize the parallel compute capability of GPUs. So in this day and age where models have reached such a massive scale, it is imperative that any mature framework support these platforms to accelerate training. Then sixth, we have the support for popular datasets and pre-trained models. Does the framework have built-in support for popular datasets, and does it come with pre-implemented model architectures for allowing us to use pre-trained weights? Then we move to edge deployment. More on this later, but broadly, we cover on-device inference in this. Then again, multi-GPU support. So as the scale of these models is huge, one GPU may not be enough. So does the framework support distributed training with something like FSDP across multiple GPUs? And then lastly, the number of models supported. So does it have built-in out-of-the-box implementation from some of the premier and cutting-edge models like RNNs, LSTMs, and transformers? So with these in mind, let me introduce the frameworks that we consider in the study. We begin with proprietary frameworks, which includes Neural Designer by Artelnix. So coming in at around a subscription of around $7,000 a year. It's a GUI only, no code, beginner focused platform that allows you to train basic ANNs. Then we have MATLAB with its deep learning toolbox, which of course integrates into larger MathWorks MATLAB ecosystem. Then on the open source side of things, we have TensorFlow by Google, which is one of the most mature frameworks in the market, being deployed on an absolutely massive scale by Google itself and a few other companies. Then we have PyTorch by Facebook. It's a research first framework being widely used in academia. Then we have Deep Learning 4J by Eclipse, which is the only Java virtual machine option, a mature framework for the JVM. Then we move on to some of the historical obsolete frameworks like Theano, which is no longer under active development, and Cafe, which of course is too not under active development and was built with speed and modularity in mind with a focus on images. So with that, we move to our comparative analysis, beginning with qualitative analysis. So the qualitative analysis is presented in the form of a comparison table, which you can look at in detail here, but I'll summarize some of the main findings. So as is evident, TensorFlow and PyTorch tick almost all the boxes, providing across the board, providing support for all the premier models and being under active development, supporting a large number of computing platforms. So they provide well-rounded performance in terms of our qualitative analysis. And Neural Designer, on the other hand, only supports CUDA and is under active development. So it supports none of the premier models in the market right now and does not have a support for a lot of the developer experience toolkits. So you can take a look at this in detail here. And then for our quantitative analysis, we conduct a literature review, which I'll summarize here again. So in a head-to-head comparison between TensorFlow, PyTorch, and Theano proved to be about 4 times slower than the two frameworks. In a comparison between PyTorch and TensorFlow, PyTorch was up to 25% faster in training time than TensorFlow, although TensorFlow provided higher accuracy by a huge margin. Again, in a comparison between these two frameworks, TensorFlow provided around 8 percentage points of difference in model accuracy, being 8% more accurate with the same architecture and same dataset. And when TensorFlow and Deep Learning 4J were compared, Deep Learning 4J was not only much slower, but also required a large number of boilerplate code. So its developer experience was much worse as well. So with all of our analysis in mind, we can move to our conclusion. And before we do that, we have another important aspect, which is the mobile and edge deployment. So here we only consider on-device inference. So now, as this computing power of low power devices increasingly, instead of communicating with the server to generate model outputs, devices are performing on-device inference. This is done mainly for real-time applications like AR/VR devices or smart wearables, where reducing latency is very important. So we now analyze whether these frameworks support on-device inference on edge deployment cases. So as again is evident, TensorFlow and PyTorch provide well-rounded performance and well-rounded support for edge deployment, being supported on iOS, Android, and embedded platforms as well. One significant difference, however, is that PyTorch allows you to create custom ports. So it allows you to create a custom platform abstraction layer, or PAL, which is quite easy to do to port it to a custom platform. However, this is quite difficult to do on TensorFlow. So that is something to keep in mind. And DL4J, on the other hand, supports only Android, and even then it requires large linked libraries, which makes it difficult to deploy in resource-constrained environment like smart wearables. And lastly, MATLAB 2 has limited support, limited architecture support, and of course, custom ports are not available due to its proprietary nature. So with that, we move on to our conclusions that we make from this analysis. So firstly, given that TensorFlow consistently provides higher accuracy, even with the same model architecture, we can say that it is a production-ready framework and is suitable for deployment, for user deployment. PyTorch, however, its superior speed allows for rapid prototyping. So, and its large research community makes it viable for research use cases as well as rapid experimentation. When compared with these two frameworks, DL4J stands out as a worse choice, but it can be relied upon when the pre-existing software stack relies heavily on the JVM, because it is the only mature framework for the JVM. Again, compared with these two frameworks, MATLAB, while it is a strong framework, its cost makes it hard to justify alongside these alternatives. Cafe and Theano, their lack of active development limits their use cases to legacy code bases, where porting them to a different framework might be difficult. And Neural Designer, with its limited support for models, may be suitable for education and learning basic ANNs, but its steep price again restricts its use to well-funded higher education institutes. So with that, my presentation comes to an end, and of course, I'm open to any and all questions from the panel.
Yeah, so nice presentation. So I don't have any questions, but I have a suggestion. Instead of this generic comparison, you could have
Right.
done this comparison for a specific domain. Maybe all these infrastructure or frameworks or all these for one of the domain, like maybe for healthcare, for agriculture, for whatever area you like. You could have done that. That would have added some value.
Right, ma'am. So this is the one of our future scope of the work that this is something that I am personally doing as well. So comparing reinforcement learning frameworks. So as deep reinforcement learning is coming to the forefront, there are many frameworks available for that as well. So a comparison in terms of these parameters for those frameworks might be useful and is a future scope.
Dr. Panipam, do you have any questions for our speaker?
No, thank you.
Thank you.
Okay, thank you so much for your presentation. Okay, our next speaker is Kevin Sinchi from the Salesian Polytechnic University in Ecuador. And the title of his paper is Optimizing Academic Performance Prediction, a crisp MLQ-based approach using multivariate analysis and ensemble learning. Kevin, I request you to kindly unmute and start presenting. Okay, I don't think he has joined, so we can move right ahead. Our next speaker would be Mailusi Inusa from the Malawi University of Science and Technology in Malawi. And the title of his paper is Predicting Participant Attrition in Pediatric Clinical Trials Using Machine Learning and Deep Learning Models. Sir, I request you to kindly unmute and start presenting.
All right, thank you, moderator. And thank you, session chair. So let me share my screen. Yeah, I hope you are able to see the screen.
Yes, the screen is visible. You can start.
All right, thank you. So as introduced, my name is Mairos Inusa. from Malawi University of Science and Technology. And today I'll present our work on predicting participant attrition in pediatric clinical trials using machine and deep learning models. And this is a joint work, and my co-authors are Dr. Priscilla Maruichi and Professor Clement Nyirenda. So I have organized the presentation into 5 sections. So we'll start with the introduction, then we'll go to methodology, results discussion, then we wind up with the conclusion. Now we'll start with why this topic is significant. So we define attrition as a participant dropout or withdraw from a clinical trial. And this is one of the challenges faced by researchers in clinical trials. So looking from the data, the reported rates, they range from 3% up to 63%. When the attrition goes up to 20%, it now becomes a concern. This is so because the high attrition, it causes the increased cost, longer trial duration, reduced statistical power. It also biases the outcome. Also, it makes the future requirements difficult, and also it leads to loss of trust. So the clinical trial researchers, they employ a number of strategies to reduce attrition, such as offering incentives, strengthen the communication between the staff and the participant. Also, they show the respect to the participant. However, the success of these strategies, they depend on a specific context. Now, we have seen that with the rapid increase in application of a machine and rapid increase in application of machine and deep learning models in in clinical trials. However, the application of these techniques they are limited. The application of these techniques they are limited, so they are rarely applied to pediatric clinical trials. And also, we have noted that the clinical trial data set they suffer the class imbalance, as well as they are also limited in sizes. So these they lead to poor predictive performance. Now, with that, we have set our objectives. So number one, we're going to develop and also evaluate machine learning models to predict attrition in pediatric clinical trial. Number two, we're going to compare the data enhancement, which is a SMART GAN, as well as the combined augmentation. Lastly, we're going to identify and rank the influential features for attrition. Now, looking at our methodology, so initially we started with 2,168 participants aged 6 months. Out of these, we had 18 deaths, and we excluded them only to concentrate on attrition analysis. We also selected 14 features using domain knowledge. And these features include the child age, residential area, maternal age, education, occupation, as well as the adverse event. And our data set was imbalanced. As noted, we're having 81.4% completers and 18.6% attrition. We processed our data set in this way. So for missing values, we used KNN imputation. So we chose this because it preserves the data integrity. For outliers, we identified them using plotbox, and we capped them using winsorization. For categorical values, we handle them using one-hot encoding, and then we normalize the numerical features using min-max normalization. We also we used for classifiers, logistic regression, random forest, MLP, as well as 1DC NN. So we split our data set into 70 training and 30 test set. And out of those 70%, we hold out 10% of the training data set for validation. Now, after preliminary runs, as well as the results from Absolute Sharp, so we selected top 8 features out of 14 to train our models. So we also trained all the 4 models, and for data settings, which is the original data set, the smart enhanced data set, the GAN enhanced data set, as well as the combined data set. We evaluated our models using F1 score as a primary metric, alongside with precision, recall, AU log, accuracy, and confusion matrix for full insight. Now, here are the results. So the results are just modest, and the range, the F1 score ranges from 0.54 to 0.51 across all models and the data setting. And we noted that random forest was the best under smart enhanced, and it scored 0.514. We also noted that on data augmentation, we also noted that SMART has improved both performance of random forest as well as the performance of MLP. On the other hand, the GAN as well as the combined enhancement, SMART and GAN, did not improve our models. So it led to increase in a range of 0.0013 to 0.037. Now, this is the overview of how our models performed. So the blue one, the blue color here, it shows the performance on original data set. And the orange one here, it shows the performance on combined enhanced data set. So here you see that on the original data set, SMART was the best. I mean, random forest was the best. And on the SMART enhanced data set, you see that also random forest was the best. And on GAN enhanced, so you see that here, logistic regression was the best. And on combined, here you see that, yeah, sorry. So for GAN enhancement, you see that 1DCNN was the best, and therefore combined, you see that logistic regression was the best. And one more thing that we have noted is that there is a great improvement on MLP performance when SMART was applied. So you can see that the original was 0.4487, but after applying the SMART, it improved, pushed the performance up to 0.5053. So here is the table showing the overview of how the best performing models on each data set performed on the other matrices. So here on the original data set, and as you said already, that this random forest performed better. So you see that it scored the precision of 0.5489, and AU log of 0.584848. For SMOT, random forest again is scored here a precision of 0.5557 and a log of 0.5874. And on GAN enhancement, you see that 1DCNN scored a precision of 0.517 and a log of 0.5296. And on combined
Excuse me,
enhancement,
sir.
yes.
Apologies for interrupting, but you have 2 minutes of presentation time left.
All right.
Yeah, thank
Okay,
you so much.
so all right, thank you. So I think we can just go. You can just go to straight to our discussion. All right. So for our discussion, so we noted that the London forest, combined with SMOT, showed the lead promise for identifying participant at risk of dropping out with a recall of 61.7 on confusion matrix. So I think this could help the trial team to target support. Interestingly, we also see that the MOP benefited a lot from SMOT. So this shows that this MOP it is sensitive to colors imbalance. And GAN here has shown the poor performance, so it did not help the performance of the models. So I think this is due to mode collapse instability, low quality synthetic samples. And we also ranked our features, and we see that we've seen that residential area was the highest. So I think this is due to difficult to access to the healthy facilities in low income countries like ours, due to maybe a transport as well as a relocation. So here also we noted that the caregiver factors had more influence than the broader economic features. Now, to conclude, so we have this. To conclude, here is the contribution. So this is one of the first research to predict pediatric clinical trials using machine and deep learning models. And also it showed that the London forest was the first. London forest showed a clear potential for predicting dropouts in this context. And on the argumentation, we also noted that SMOT has helped a lot. And on the influential factors, we've seen that residential area, adverse event, and maternal factors were among the first influential factors. Nonetheless, we have some limitations. So we used the data from a single country, so we cannot generalize this to other settings. And also, we did not include all the drivers of attrition, like trial complicity, relocation, and media influence. And we did not conduct an external validation. And also, the performance was just modest. So we plan in our future work to expand this to a multi-site dataset, and also to incorporate more known factors for attrition. And also we plan to test more additional machine or deep learning algorithm, as well as some techniques to boost our accuracy. So this is the end. Thank you. If you have questions or comments, please, you're welcome. Thank you.
Yeah, no questions from me. It's a nice presentation. All the best.
All right, thank you.
A nice presentation, and I have no questions.
All right, thank you.
Okay, thank you so much for presenting, sir.
All right, thank you.
So our next speaker is Wu Min Tan Nguyen. Apologies for mispronouncing your name, sir. But the title of his paper is Refine Verilog, Reliability-Based Fine-Tuning and Inference Enhancement for Small Language Model in Partial Verilog Generation. Sir, I kindly request you to unmute yourself and start presenting.
Hello, I'm Vũ Minh Thành Nguyễn, and I'm see that you have mentioned me, right? Screen share now.
Sure, sir, you can.
Okay. So, can you see my screen share?
Yes, sir, your screen is